Okay, so we're almost at the end of this chapter. We just have to practice a few more, look at molecular geometry, re-emphasize what we just learned about it, and then look at polarity and symmetry. Alright, so bringing it all together. Draw the Lewis structure, the best representation for TeF5-, and provide the molecular shape. Let's do that. So the first thing you do is count valence electrons, of course. Tellurium is right in the sulfur group, chalcogen, so it has 6 valence electrons. The 5 fluorines each have 7, and there's a charge, so we add an electron to it. Add it all up, and you end up with 42 valence electrons. Put tellurium in the center. Fluorine cannot double bond, so that's a nice little thing to know. Put the 1, 2, 3, 4, 5 there, so and it doesn't matter how you draw it. It doesn't have to look three-dimensional at all. So you just used up 10 electrons to make 5 bonds. Oh my goodness, I put iron in there, huh? Okay, well, it's very late and I really want to get this done, so you'll just have to suffer through this with me. Oh, hey, I meant to put an electron there, right? You put all the electrons in. Okay, and you should verify that, make sure that I have all the right electrons, but I am not even counting them right now, right? I could have done that without calculating the 42, just guessing, right? And so now comes the time when I double check. I look at the formal charges. I know I'm supposed to have a negative charge, so I need to be careful there, right? I also know that fluorine, if I have a valence of 7 and 1 bond and 6 lone pairs, singly bonded terminal, I'm always going to have a formal charge of 0. Okay, so that's 0, 0, 0, 0, 0. Alright, if that's true, I'm going to have that negative charge on the tellurium. Now let's check, right? So tellurium right now has a valence of 6. There are 5 bonds, so that's minus 5. So that would give me a plus 1. Okay, so that's not correct, but I can fix that by adding a lone pair. Okay? And now it has a negative charge because now I have minus 5 and then minus 2 for the lone pair, right? It's 10 bonded electrons and 2 from the lone pair. So that's where the 5 comes from, and then I added the lone pair to make this negative 1. So that's just a different approach, or you could have just simply counted to 42 as you go, and when you filled up the last fluorine, you would have automatically put the tellurium on there. Okay, so now we're going to look at molecular shape, right? So electronically, this is an octahedral, and removing one of the atoms and replacing it with a lone pair is going to make it square pyramidal. I don't know why this is glitching more than normal. Okay, COF2. Okay, well, COF2. Carbon, oxygen, fluorine. I already know fluorine is going to be having 6 lone pairs, and then if you draw enough, you'll see right away carbon's going to need 1 more. It's probably not a lone pair. Oxygen will have a negative charge if it's singly bonded with 6 lone pairs. I'm sorry, 6 lone pair electrons, 3 lone pairs. And so this would really be it. And so it doesn't have an overall charge. It's just COF2, no charge, 0, 0, 0, 0. Carbon is 4 minus half of 8, which is then 0. So all our formal charges 0. This is trigonal planar. Okay? Alright. Couple more here. 3 more ICl2. Let's go count valence electrons and do it the proper way this time. Iodine is 7 plus 2 times 7 for chlorine plus the 1 is 24 okay, so 22 valence electrons, right? So it's 3 times 7 plus 1, it's 22 valence electrons. The most electropositive is going to be the one lower in the group. They're both in the same group, so it's the iodine. I get 2 chlorines that are towards the outside. Group 7 means if I have a single bond terminal, then these would all be 0, and so iodine gets the other 3. So the electronic shape for this one is, of course, a trigonal bipyramid, but the molecular shape is linear. PCl6, 1, 2, 3, 4, 5, 6, chlorines around it, all with, again, same idea as here, singly bonded. I'm waiting for it to glitch out on me. Hasn't done it yet. Shall I praise it? Weird. That's just my technique, I guess. Right, so this is all good. Everything is 0. Let's check phosphorus as well. And of course, phosphorus has a valence of 5. And so minus 6, which is going to be minus 1. And we expect that because there's a minus 1 charge. This is simply an octahedral. I think we already drew SF4, we drew SF4, this is SEF4, SEs in the same group. So it's going to make that same shape, a seesaw. F, 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 F. Okay, fluorine, fluorine, fluorine. And I'm putting in these electrons because I expect you to do the same. This is important. We must make sure everything has an octet. Of course, selenium can have an expanded octet, which it does here. And so this is also a formal charge of 0 here, right? We have 6 minus half of the 8 minus 2 for the lone pair, which is 0. So selenium is also 0, and this is a seesaw as a molecular shape. All right, let's take a look at something else. Let's revisit the dipole moment, right? We already know we can have a polar bond if 2 nonmetals that are forming a covalent bond have a large difference in electronegativity, more than 0.4. Then we have a polar bond. Okay, and so oxygen-hydrogen has a polar bond. Carbon-oxygen is also a polar bond. Right? Nitrogen-hydrogen is a polar bond. Sulfur-fluorine is a polar bond. Carbon-hydrogen is not a polar bond. The difference is 0.4. So this is not a polar bond, so we don't even have to worry about symmetry here, right? This is a polar bond, and I'm drawing the arrow towards the more electronegative element. But just because there are polar bonds in a molecule does not mean that it overall has a dipole moment. You have to look at all of the polar bonds together, right? And the best example here and the easiest one to see is carbon dioxide, which is this. And I should really have those lone pairs in here, right? And I'm risking glitching, but this is linear, and so there are 2 polar bonds that cancel each other out. So the symmetry here, molecules that are highly symmetrical can cancel, the dipoles can cancel each other out, just like here. This is linear, and the bonds are of equal strength. The polarity is of equal strength. So this is overall not symmetrical, whereas because water is bent, it is symmetrical, it is polar, and carbon dioxide is nonpolar. It has to have an overall dipole moment. This is polar because there's a lone pair here. This is pyramidal, it pushes down on it. And this is a perfect octahedron. All of these angles here are 90 degrees. And so this is nonpolar, although it has polar bonds, okay? So this can be a little tricky, but so you basically just look at symmetry. So, right, so we have this electron cloud. Water is the example here. We have a large difference in electronegativity, larger than 0.4, and it is so the overall dipole moment is this way here, right? So if you look at that, so you've got that negative charge and the positive charge, so to speak, here, right, in this electron cloud. If this was linear, that charge would come over here and it would cancel each other out. But no, this is polar. So this is nonpolar because it's symmetrical. This is also nonpolar because it's symmetrical. It's trigonal, planar, and these strong polar bonds, they just cancel each other out. So symmetry has a lot to do with it. Alright, so this is sort of kind of almost it. What I have here is a summary for the different molecular shapes. Sometimes it helps if you can't visualize it, you can memorize this. I'll kind of fly through it. This is then up to you. Okay, so you can put any molecule such as water, for example, H2O, once you've drawn it. Let's draw it over here. Oops, okay, let's just put it lone paired like this. This is fine. We have a central atom, so this would be A. Everything's A, and then it's B something, E something, right? Okay, so A is the central atom. In this case, that's the oxygen. B are the bonded atoms, right? So here we have two bonded atoms. It's that little 2. So it's AB2, and then E are the lone pair electrons on the central atom. So you've got 2 of those. So it's AB2E2. And AB2E2 is always bent, no matter what. Okay, all AB2E systems are always bent. H2S is the same thing. It belongs to this category. Its molecular shape is always going to be bent, and that helps some people, right? So if we go through this, AB2 is always linear, right? You've got enough, I had it on the previous slides, a central atom with 2 bonded atoms, no lone pairs, it's always linear. Moving on to occupancy 3, meaning electron regions, so electronically it's always trigonal planar, right? Occupancy means total, it's X and E together. If you have, it's B and E together, right? You have A, B, E. Right, if this was X and this was Y, it's X plus Y. I think I have that on the other slide, right? Yeah. X plus Y is occupancy. I just kind of rushed over that, right? So that's the pairs of electrons on a central atom. So something that's AB3, like BF3 from the previous page, or this here, C, H, and then it has 2 CH3 groups. I don't want to spend too much time here. That central atom here has a trigonal planar shape. It's an AB3 system. You replace one of these with a lone pair, it's going to be bent. Example, SO2. Remember, SO2 has 2 double bonds because it can have an expanded octet, but also a lone pair on sulfur, which pushes that down and it falls under the category AB2, right? 2 bonded atoms and 1 lone pair, AB2E. Looking at AB4, tetrahedral, there are several examples here. Phosphate, sulfate, perchlorate, they all have no lone pairs and 4 bonded oxygens. They are all tetrahedral. If you replace one of them with a lone pair, we have several examples here, all shown underneath. All of these are examples of AB3E, which are all pyramidal. And if you remember, a perfect tetrahedron has a bond angle between atoms that is 109.5 degrees. Now it makes sense that if you replace one of the atoms with a lone pair, and I told you that it needs more space, that would push down, right? So I'll come back to this in a minute. So it would be less than, if you replace it, any of these are less than 109.5 because it can push down. But it seems, just looking at these different bond angles, it looks like the angle can actually decrease drastically or less. And so that has to do with the polarity of the bonds. But before I explain that in more detail, let's look at a nice little graphic here of what happens when an atom is removed and the lone pair of electrons are no longer tied up as an electron cloud, right? So let's represent this, the nitrogen nucleus here, and this is the hydrogen nucleus of one of these bonds. Let's say this one here, right? Because that's the one I'm removing. So this electron cloud, what I drew here in red, is actually this blue sphere, right? And although that's slightly polar, it is fair to represent it as tied up, okay? Now, once you remove this hydrogen, these electrons flop down, right? So the hydrogen here is removed and the electron cloud spreads out. So this electron pair, that's just abbreviated with two little dots, actually presses down, decreasing this angle. This was 109.5 here to about 107. Okay, so now let's go back here and think about what's happening. This can be a little tricky for some. Okay, so what we need to look at is the polarity of the bonds also matters. Nitrogen has an electronegativity of 3.0. Hydrogen has an electronegativity of 2.1. So this is definitely a polar bond, right? So where the electron density is pulled towards the nitrogen here, right? This is the more electronegative element. Electron density is pushed towards it, right? Okay, now what happens when you go to phosphorus? Phosphorus is right underneath. It actually has a drastic drop in electronegativity to 2.1. So now we no longer have polar bonds, and some of that electron density can be pushed away from the bonds, which allows this lone pair to press out and decrease this angle drastically. Look at the big difference in angle here. So these bonds have polarity that's pulled towards the outside comparatively to the ammonia one, where the ammonia pulls electron density towards the nitrogen, not allowing this lone pair to push down. Now, some of you may remember that when you go down to the fourth and the fifth group, the drop in electronegativity is not quite as drastic anymore. In fact, here's a difference of 0.9, and between arsenic and phosphorus, which arsenic is right underneath, phosphorus is just 2.0, so the difference here is just 0.1. Therefore, your angle doesn't decrease a whole lot more than it did already. And then, of course, we also have a size increase of arsenic. But more importantly, it's the polarity of those bonds. And then antimony is also one further down, and it's just, again, just 0.1. So the polarity here is differences. The polar bonds are about the same. And so there's just a little bit of a drop in electronegativity. The same argument can be made for these here, right? So here we have nitrogen, as I said, it's 3.0. And it is actually the fluorine that's much more electronegative than chlorine, which means this electronegativity is pulled away from the bond and here, and so this is going to allow that lone pair to squish or push down further, right? And so chlorine has an electronegativity of 3.0 and fluorine has a negativity of 4.0, right? Allowing that electron density to be away from the bonds, away from the nitrogen. Same argument can be made here. Now, I don't want to beat this horse to death. Let's just keep going. Moving on to occupancy 4. We still are in occupancy 4, but now we're going to replace another bonded atom with a lone pair. So this is water and hydrogen. It's S2O, huh? Okay, I guess. There might be some problems here, but I'm not going to worry about it yet right now. It's H2S. It's H2S and H2SE. Not sure how I could have missed that for years. Anyway, they're shown down here anyway. And so same argument here. First of all, it's bend. We have occupancy 4. So electronically it's a tetrahedron. But the angle is no longer 109.5 the minute we allow these lone pairs to spread out. And so the same argument is made here about polarity. When you go to sulfur from oxygen, polarity can be pushed this way. The bonds are less polar and electron density is pulled away from the central atom. Almost done. Okay, this is just a summary of the bonds here for occupancy 4. And here we have no lone pair. This should be 109.5. No lone pair, one lone pair, two lone pairs. So there's also something to be said about having two regions pressing rather than one region. Okay. Going to occupancy 5, we know that trigonal bipyramidal. And by the way, forget these things for now. Don't ask yet. That goes into the next chapter, which deals with valence bond theory. Okay, so valence bond theory deals with that, and so don't worry about what I have behind the occupancy here. So AB5 is trigonal bipyramidal. Seesaw AB4E. I'll let you just kind of deal with this yourself. You can either draw a molecule like I3, and when you're done, you can put it into that. You can either visualize and say, okay, this was a trigonal bipyramid. All three lone pairs are going to be in the equatorial position, therefore it's linear. You know, if you can visualize that and deal with that, that's great. Or you draw it and you stick it into this memorizable category and you say, okay, we have a central atom, we have two bonded atoms, and we have three lone pairs. Right? Okay, so this is AB2E3, which I'll memorize to be linear. So you can either memorize that or figure it out. One way or another, you're going to have to figure it out. Okay. And then finally, we have occupancy 6, which is AB6, and then you remove one of the bonded atoms with a lone pair, so you have AB5E and then AB4E2, which you go to a square pyramid, and then you go to square planar. And this is it. This is the end of chapter 5. This is the halfway point. I have 5 chapters left. Chapter 6 will be recorded next. Have a great day.